Okay. Well, welcome everyone to another TCS Plus talk. Today we're very lucky and excited to have Venkat Guruswami from UC Berkeley, who will tell us about a near cubic lower bound for locally decodable codes. And before we begin, I guess just a few administrative things. We are recording the talk, so we'll post it later on YouTube. After the talk, there will be just like a short session just to hang out and ask questions with Venkat and discuss anything from the talk. And I do want to encourage people to keep their cameras on to give some visual feedback to Venkat, and feel free to unmute yourself, or I'll also be monitoring the chat in case there are any questions. But with that, Venkat, please take it away.
Okay, thank you very much. Yeah, it's a pleasure to give another one of these TCS Plus seminars. So today I'll be talking about a lower bound on the encoding length for 3-query locally decodable codes. I'll define all these things as we go along. And what is nice about this work is also it really was inspired by progress in constraint satisfaction algorithms, specifically algorithms to refute random-ish instances of CSPs. And this is joint work with Omar Al-Rabia, Pravesh Kothari, and Peter Mano. Okay, and as Eric said, if you have any questions, feel free to just ask online as we go along, either in the chat or by unmuting yourself. Okay, so just a brief primer on ECCs may not be necessary, but just to set up notation. So we're going to have a message which the encoder is going to encode into a longer string called the code word. And the reason is that there is going to be some noise which corrupts the code word into some distorted string. And the hope is that the inbuilt redundancy in the code word allows a decoder to figure out where the mistakes must have happened, correct the code word, and recover either the code word or equivalently the message M prime. So our goal is, of course, to have M prime equals M. And a very important parameter in codes is that we don't want to, we are incurring a blow up here. We are sending K bits to, or K symbols to N symbols. So first of all, the symbols, throughout this talk, I'm going to focus only on the binary alphabet. So sigma is 0, 1 for the talk. There are some very interesting challenges for large alphabet Ks, and I might mention at the end, but really just think of it as bits. And so K is the number of message bits, and N is the number of code word bits. And we would obviously like N to be not much larger than K. And in traditional coding theory setting, this is measured really by the ratio K by N, which is called the rate. But as we will see in our setting, N really cannot be proportional to K. So we will just think of N as a function of K, and how big does it have to be? Okay, and so the question is, there are various noise models people study in coding theory. And for this talk, we'll be in the worst case noise model. So we'll assume that a small constant fraction of bits can be flipped, some delta fraction of bits. And you can really, throughout the talk, delta will not really figure much at all in the talk, except in the back, it's just some small enough constant. So we want it to be bounded away from 0, but we won't be too picky on how big it is and so on. But that's the model. But the crucial thing is that it is worst case errors. So the noise, the bits can be flipped wherever at any. And a common class of codes are linear codes, where the encoding is simply a linear map. And in some sense, we will see that linearity is going to play an important role in this thing, even though the results apply for general codes. Okay, so hopefully this setting is clear. So what are locally decodable codes? So in a traditional setting, you have a message, you encode it into a code word, some bits get flipped, and the decoder is going to read the full noisy string Y and try to recover what the message M is. Okay, that's the conventional setting. And you get the full message. But locally decodable codes are motivated by, what if I only want, say, the third bit of the message? So in this case, of course, you can still do the same thing. You can decode the full message and output the third bit, but that seems wasteful. So if you only want a specific bit of the message, can you do this much faster? In particular, can you do it in sublinear time without reading the full received word? And perhaps you could even do it in like constant time. And the best way we're going to sort of to formalize this instead of time is to look at the number of queries the decoder is going to make. decoder will only look at a small portion of the code word or noisy word and try to recover what the message is. So for example, so you have the message and this noisy thing. The idea is that the decoder will be given as input an index I from 1 to k. And the goal of the decoder is to find out what m sub I is. Right? And the decoder will make some queries into the noisy word. The queries will be picked from some distribution. And based on those bits, it's going to make an estimate on what the ith bit is. And our goal is to, of course, for the ith bit to be equal to mi, the estimate. But since you're only looking at a very tiny portion of the received word, and there might be errors there, and you cannot get this with certainty. So the idea is that you allow some probability of error. And let's just say, again, this will be another parameter, which won't be too important in the talk. We'll just say that you get mi hat equals mi with probability bounded away from 1/2. Okay, half plus gamma. So that is the object of interest. An LDC with parameters q, delta, gamma is basically a code which has an associated decoder which only makes q random queries to an n-bit string, suppose a code word. And regardless of the message and regardless of the index, it should output the correct message bit with probability half plus gamma. And this should hold no matter where the errors are. So this should hold for any string y, which differs from that code word in at most delta n places. So these are the three parameters: number of queries, the number of errors, fraction of errors you correct, and your confidence as of the estimate. And as I said throughout the talk, really delta, gamma won't really figure too much. Just think of them as small enough constants, but bounded away from zero. Okay, so that's the idea. Again, I have the same definition here. Hopefully the definition is clear. So you're trying to figure out a single message bit by making few queries. One thing, of course, you might think is that, oh, why don't I just place the message bit somewhere in the code word and the decoder can look at it, or maybe make many copies of it. And of course, the problem is that this is worst case errors. So if you make 1,000 copies of the first bit, the adversary might corrupt all those copies or most of them, and then you would make a mistake invariably. So somehow you have to spread out information about each bit uniformly in the code word, and we will see this intuition formally later. Is the query always about revealing a bit of the code word? Yes. So the goal is to find out a particular bit. The queries, the set of queries you make depend on which bit you're interested in. Okay, I don't think I fully understood the question, but I think that's hopefully the answers. So what's the extreme locality? You can try to do it with one local query, just one query. And in this case, pretty much the only thing you can do is what I said, just repeat the message bits many, many times. But since you can really delta n of the copies could be, delta n of the bits could be wrong, you really have to repeat each bit delta n times or more to have some robustness. And that effectively forces k to be 1 over delta. So you really cannot have growing message length with one locality. And again, to remind you, we would like delta gamma to be some fixed small constants and k and n to grow. Okay, so that's the setting we are interested in. But already 2 local is possible and interesting. Okay, so there is a classic code called the Hadamard code, which achieves two query decoding, as I'll explain now. So what is the Hadamard code? It's a linear code. It's a linear map which maps m, and essentially it outputs the dot product of m with every possible k-bit vector. So in some sense, the most redundant linear code there is. Okay, it takes every linear combination of bits of m and outputs it. You can pictorially see this as all the hypercube, and it takes a message, dots it with every point in the hypercube, and outputs the thing. You can imagine the bits sitting on the vertices of this hypercube, the k-dimensional hypercube, which has 2 to the k vertices. And why does it have some nice locality? So the thing is that if you want to figure out what the ith bit is, the ith bit is m dot ei. You can get this as m dot r plus m dot r plus ei for any r. And this motivates a very natural 2-query decoder. Pick a random point r and try to read the noise, the word y at the location plus ei, and then XOR them. Plus throughout the talk means XOR, and that will give you an estimate. And the point is only delta fraction of these blue points are wrong. So the chance that one of these 2 points is wrong is at most 2 delta. So your estimate is correct with probability 1 minus 2 delta. Okay, so that's the classic 2-query decoder. Okay, for Hadamard codes. Now that's great, but as we will see, the length of that code is very big. And before I go to that, I want to give a little bit of history on locally decodable codes. I'll be brief here. So locally decodable codes were implicit and actually played a very important role in work in the late 80s and early 90s on self-correcting computation, random cell production, which eventually those ideas led to interactive proofs and PCPs. So it was very influential theme at the core of a lot of those developments. It was explicitly defined and studied a bit later by Katz and Trevisan in a paper in 2000, where they also gave the first lower bounds on these codes, a very influential paper. And just to give a sort of a big list of where all LDCs figure, as I said, they figure in PCPs. You can use locally decodable codes to take a function which is hard in the worst case to give a function which is extremely hard on average, which then downstream has many applications in de-randomization. A certain form of LDCs are really what are at the core of private information retrieval, very intriguing notion in information theoretic cryptography. And in general, it gives a new lens on sublinear algorithms. There is a sort of cousin of LDCs called locally testable codes. And one could say that that really spurred the whole field of property testing. And locally decodable codes are a very good instance of sublinear algorithms. And it's a very basic object in complexity. It has many algebraic connections to rigidity, polynomial identity testing, and so on. And also, you can imagine there's also connections to data structures, where if you want data structure errors, that has some tight connections to LDCs. And the last thing I'll mention is this potentially more sort of practical use of this is really in distributed storage, where we store our data on the cloud, and we might want a particular piece of the data quickly. Or the data might be split in many servers, and one server might go down, and you might want to recover it quickly without seeing too much of the code. And that is indeed a very practical case which is deployed and in use. But I will give the disclaimer that for those applications, the rate has to be high. And so it's not locally decodable codes, which are really important. It's locally recoverable codes, which are very similar, except you just assume there are very few errors. So it's a sort of a different regime of the same concept. So you correct very few errors, so you're able to have much higher rate, but the spirit is the same. Okay. So I apologize for not giving. There's lots of exciting works and citations to give here, which I skipped in the slide, but it's a very central notion.
Venkat, the question about the previous slide, actually, the Hadamard code. So you said only delta fraction of the points are corrupted, but how is that true for worst case? I'm a bit puzzled. Like for a single message, the adversary can corrupt all the points, right? Because it's—
Oh, yeah. So it's very crucial that this R is picked randomly. So no matter what I is, the point is that these 2 points are correlated, but they're individually random. So delta fraction of these, imagine these blue points as being red if they are an error. Delta fraction of the hypercube is red. You throw a random point, you will be wrong only with probability delta.
I see.
So the chance that YR is different or YR plus EI is different is each at most delta. So you add them up by union.
Okay, that makes sense. Thanks.
But that's the whole point. So the thing is that you're spreading your queries sort of uniformly across the code. And therefore, wherever the errors might be, the chance that you hit the errors is low. Okay, so this theme will play out. Okay, so can you amplify the probability of correctness for MI? Yeah, I guess one way is just to repeat the decoder many times, but of course that will increase the number of queries. Yeah. But without increasing queries, there might be some inherent trade-offs between delta and gamma and so on. And I view those as sort of secondary trade-offs, which will not figure in this talks.
Yeah. So for every locally decodable code, you cannot amplify. Like if it is based on randomness, then you can amplify, is it?
Yeah, no, yeah, you can just repeat the thing with fresh randomness each time, and then it just amplifies. Right? So they use usual methods. So it's just that it will blow up the queries by the number of trials.
Okay.
Yeah, that's the problem. Yeah. So. Okay, so the object of this talk is how long do locally decodable codes have to be, right? So the Hadamard code was excellent. It had the minimum number of possible queries, 2 queries, but it really was bad in the sense that it blew up k bits to 2 to the k bits. So it's a really horrendous blow up, okay? So the question then becomes, if you want a particular Q, 3, 4, what is the best length you can have for a Q query LDC? Okay, that's that's a direction which has received a lot of attention and is also the subject of this talk. Now, for a long time, sort of the main kid in town for LDCs was this codes called Reed-Muller codes, which are essentially like a higher degree generalization of Hadamard codes. So you take multivariate polynomials of some bounded degree, and you evaluate at all points in the cube. So if you have an m-dimensional cube, evaluate it at all points. So earlier D was 1 and M was K, but you can imagine other combinations. And then you get locality, because if you take a multivariate polynomial and restrict it on a line, then you get a univariate polynomial of much shorter length. Okay, and this really was the principle which drove a lot of the early work on LDCs. And you can play with different choices of M and D, and you can get different trade-offs. For example, for constant Q, constant number of queries, you get N, which is exponential in K to the 1 over Q minus 1. So for Q is 2, this is 2 to the K, Hadamard codes. For Q is 3, this is 2 to the root K, and so on. 2 to the square root K, and so on. So that's one setting you can get. You can also make, you can say, well, I'm not going to be so adamant to make constant number of queries. Let me give myself more queries. So if you make, say, N to the epsilon queries, then you can achieve constant rate. So N will be a constant factor bigger than K, albeit a big constant factor, exponential 1 over K. And then there are some other settings like, say if Q is log N, and then you can have polynomial blow up. And this setting and the Hadamard code figured prominently in the PCP theorem proof, original PCP theorem proof, for example. So you can have polynomial blow up, but the number of queries is log N. And it's just more or less these things follow by just playing with these parameters and Reed-Muller codes. And this was pretty much the state of the art for the long time. So there was exponential length for constant queries, and essentially no non-trivial locality was known for large rate. Okay. And I just had one slide on the high rate, constant rate regime, but maybe I'll just skip this. And if there's any question at the end, we can come back to discussing this. But just the upshot here is that if you allow me to make more queries, like say 2 to the root, let's say N to the epsilon queries, then I can have very high rate. Okay, and this followed from some very nice lines of work on multiplicity versions of Reed-Muller codes, and there are also some alternate constructions. Okay, so by now, if you give me N to the little o of 1 queries, I can have excellent rate. Okay, and these codes and Reed-Muller codes, as well as all these follow-ups, also have this additional nice property that the codes are locally correctable, which means that it's not just that you can find the ith bit of the message, you can find the ith bit of the code word wherever that might be. Okay, this is a related notion. I'll just throw it out there and we'll come back to it. But for the talk, let's just focus on LDCs. Okay. Okay, so let's come back to the constant query regime, which is the focus of this talk. And in their beautiful paper, Katz and Trevisan showed that if you want constant query LDCs, you cannot have asymptotic codes. So the blow up, N cannot be proportional to K. The rate has to go down to 0. So they showed a lower bound of K to the Q by Q minus 1. Okay, so for example, for Q is 2, it was K square. Q is 3, it was K to the 1.5. So what is the smallest length you can have? And so 20 years later, we know a bit more, but still there are many mysteries. So let's see what's known. So start with 2 queries. Again, 1 query really is not much you can do. So let's start with 2 queries. So we saw an upper bound of 2 to the K, and it turns out that is basically tight. So there is a lower bound of 2 to the omega K. So you need exponential blow up. And it was shown first for linear codes and later for general codes using a quantum argument by Kerenidis and DeWolf. So that's the story. So 2 queries, we kind of know the picture. Now for 3 queries, the same work by Kerenidis DeWolf improved the lower bound to there. And in fact, let me go more to the lower bound case. In fact, they actually showed the same lower bound for 4 queries. And so even for 4 queries, you need K square. And I'm ignoring some log factors in this description. And some of those log factors were improved later by in works by Woodruff. So that's the lower bound side. So for 4 queries, you need K square. In general, for Q queries, Q even, you need these many things. And for the upper bound side, the longest time Reed-Muller was the champion. And then the striking construction of Sergei Yakanin and various follow-ups thereof have now shown that at 3 queries, something miraculous happens. You can make the length of the code can be sub-exponential, right? So it can be exponential in 2 to the root log K rather than exponential in K. So you can have sub-exponential things, and then that suddenly The prevailing line of thought was probably that exponential is necessary. Maybe you need 2 to the square root k or something. And this one broke that belief, right? So now situation became a lot more interesting. So, and that's the best, that construction is based on matching vectors, also works for larger queries, obviously, since it works for 3 queries. That was the story. And I said q even here. For q odd, peculiarly, the best bound for q odd was the same as the bound for q plus 1. So the best bound for 3 was the same as for 4, for 5 was the same as for 6. Okay, and that's was a bit annoying, and that's the way it was. Okay, so let's focus on q equals 3, which is the focus of our result. So here again, there are 2 extremes. Obviously, if you can do 2 to the k, you can, you need k at least. There is a lower bound of k square, and there is this upper bound of sub-exponential in k. And our main result is that we get k cubed. So we give a modest improvement on the exponent from 2 to 3. But perhaps the nice thing is that it sort of breaks this old bound and also shows a stronger bound for 3 queries than what is known for 4 queries. So it's sort of maybe understanding the problem a little bit better. Okay, so even if you got lost a little bit on all these parameters, really for the talk, I'm just going to focus on 3 queries where there is a lower. So the previous lower bound was k square, which was also the case for 4 queries, and we improve it to k cube. And again, the constant, I'm hiding factors depending on delta gamma, and indeed I'm hiding some polylog factors as well. So it's near cubic lower bound. Okay, so that's the result. So 3 query LDCs need cubic lower bound. Okay, so now I'll give you some details about LDCs and their lower bounds. Okay, so good time for probably a quick question if there's any.
So for the 2 query LDCs, is the question interesting to find out the constant in the exponent?
Yeah, I wondered about that. Yeah, probably it is. Or maybe one can really get tighter result, stronger bounds. Yeah, that might be interesting. And maybe also related to Sumega's question on like the trade-off between delta and gamma and stuff. So there might be. And I'll actually show more or less the full proof of the 2 query thing in the talk. We'll see how we do on time, but I think there might be time. Okay, so the key to start thinking about a lower bound is to somehow understand how LDCs look, right? And it turns out they have a very nice structure. So this is the old picture I had. You have a code word, a noisy version. The decoder probes it in q random places, gets an estimate. Okay. Now it turns out if you have such an LDC, it must have a very nice structure in the sense that if you write down the code word bits like in this sort of as vertices, so the bits reside on the vertices for any code word, it turns out if you have an LDC like this, this structure there must be a hypergraph matching basically a set of disjoint q tuples of positions such that if you want to get and there is one such hypergraph for every index I, such that if you want to recover mi, the way you do it is that you go to one of these hyper edges at random and XOR those bits, and that will give you an estimate. Okay, so you can partition not partition, but actually this picture is a bit misleading. Some of these blue dots could be outside, so it doesn't have to cover everything. But you must have a big matching such that every one of those edges will give you mi. Okay, and this requires a proof. But it's not a difficult proof. It's basically some sequence of reductions on LDCs, which puts it in this sort of canonical form. And I'll state the precise thing in a second. This is just a pictorial view. So you have this visual thing of a matching. And note that this is exactly what happened in the Hadamard code. If I wanted the ith bit, I took a matching in the ith direction on the hypercube, right? So these red edges are these matchings. And here it's a 2 query thing. So it's actually a graph. So you have a matching in the ith direction. And you could go to any one of those matching edges, XOR those bits, and you will get an estimate for mi. Okay. And note that if you had this structure, that is good enough to get an LDC because only delta fraction of these points will be wrong. And if you're matching and delta is small enough, when you take a random matching edge, all the points will be correct and you will get the correct answer. So having the structure definitely suffices to get an LDC, as we kind of proved for the Hadamard code. The same proof works. But it turns out it's also necessary. So it's a very nice combinatorial structure of this match. And I'll write this down formally. So essentially, an LDC implies you must have many disjoint local parity checks for each message bit. Formally, if you're mapping k bits to n bits, you must have k hypergraphs, h1 to hk, hi corresponding to ith bit. And these are all q uniform hypergraphs, which means each edge is q things. So, and with the following properties, each hi is in fact just a matching. So it looks like this, disjoint edges. And further, for each I and every hyperedge in the corresponding hypergraph, if you XOR the code word bits in that hyperedge, you will get back M. Okay, and that as happened in the case of the Hadamard code. There is a slight asterisk here in the sense that this will be kind of true for linear codes, but for general codes, if your recovery may be non-linear, you won't have this with certainty. But this will happen for every hyperedge. If you take a random M, this will happen with probability non-trivially large. So there is some correlation between this XOR and this MI for random M. Okay? And this is a normal form, which is has been around in from the beginning and a good source. So Sergei Ekanin has a survey in this now publisher series on locally decodable codes, and he spells out this, and he gives a full reduction, which proceeds in a sequence of steps down to this. So if anyone wants to refer to it. Okay. So we'll work with this point, which gives us a nice handle on how to think about LDCs. And now I'm going to make my move into random XOR instances. So the thing is, so now you have this hypergraph, each of which is a matching with these many edges, and the number of edges is going to be proportional to n. Okay, so that was actually one point I didn't maybe emphasize. It's important that the matching is large, so that if the error rate is small, it won't touch many of these edges. Okay, so that's what I put alpha in here. So you have many of these things. In this picture, I've illustrated 3-query case, which is our interest anyway. And why does, and I'm now going to think of this as an XOR instance, right? Because I know that if I put bits x1 through xi, and here, really what I want is a constraint that these things must XOR to my mi. Okay, so here is the q-XOR instance or 3-XOR instance I will get. My variables will be x1 through xn, and I will have constraints or equations for every I and every hyperedge in the ith matching. I will say that if I XOR those 3 bits, I must get mi. Okay, and the mi's are the right-hand side and the xi's are the variables. So this is a sequence, this is a set of linear equations. Each matching gives you disjoint equations, but of course, different matchings might interact. So it's a complicated system. And I have k such right-hand sides. And note that an LDC says that no matter what I put on the right-hand side, what message I put, if I take this system is satisfiable, because I can just take X to be the corresponding code word, and that will satisfy all these equations. Okay, or non-trivially large equations if you take into account that asterisk, but let's ignore that. So this gives a way to rule out an LDC, is that if I can prove that for some MI, this is not satisfiable. In fact, if I can prove that for a random choice of these right-hand sides MIs, the instance is highly unsatisfiable. Right? So typically, if an equation is satisfied with probability half, right? So if random right-hand side is half. So you can hope that if I pick the right-hand sides randomly, maybe very close to half will be satisfiable, and that will rule out such an LDC. Okay, so that's going to be our hope, is to prove that such instances won't be satisfiable. And there are some unique features of this XOR instance. Note that the instance is arbitrary because these matchings are arbitrary. Okay, there is some structure in the matchings, but different matchings could be whatever. And we don't have too much randomness. We only have k bits of randomness. So I'll say a little bit more about this in the next slide. Okay. So in general, how would you argue unsatisfiability of an XOR instance? If I give you a random XOR instance on n variables, right, with 10n equations, and the right-hand sides are random, it's a simple exercise using Chernoff and union bound to prove that it is highly unsatisfiable. Okay, that's very easy. But our trouble is that we have, how many equations do we have? We have nk equations, basically, because we have k matchings, each of size omega n. So we have a lot of equations, which is good for refuting, but we don't have that much randomness. We only have k bits of randomness on the right-hand side. All the mi's in a single matching are correlated. So in this case, it's not apparent how to do a usual argument. Oh, okay. Was there a question I missed?
Yeah, I just had a brief question. You had said that if you go back a couple of slides, you said that for nonlinear codes, the guarantee is that if you do this this hypergraph construct exactly here, exactly. In the asterisk, you said that it will hold with probability bounded away
from half,
one half with epsilon away for nonlinear codes. What is the guarantee for linear codes? Just to make sure I understand.
For linear codes, if you have this, pretty much this will hold with certainty, I think.
So it will always give the correct answer.
Yeah. So linear code, the way you get a linear LDC is that you will find these hyper matching so that this happens all the time.
So then even if the message is corrupted, no matter, as long as it's delta.
Very good point. So the thing is, so that is another transformation here. I think is a good point. I have completely forgotten about the corrupted code word now. This is only in the code. So if we have many ways to recover the bit from the code word bits itself, that is it. So note that there is no corruption anymore.
I see. Okay. So I see. This is only a property of the code itself.
And I think that's all we will use from now on. The noisy word has gone out of the picture in this normal form. Because you should correct a worst case errors, I can put the code in this canonical form.
Got it. Okay, got it.
Thanks. Okay, so our inspiration now comes from, there's a lot of progress on refutation algorithms for CSPs, and in the particular XOR instances, the question is, can we exploit that? So what is a refutation algorithm? You give an XOR instance, you have an algorithm which will output a value. And the property of this algorithm is that the value it outputs is always an upper bound on the largest fraction of we can satisfy inside, called opt of sum. So it's an upper bound on the optimum value. And typically an algorithm like this works by relaxing the problem. So instead of allowing just +1 vectors, it might values, it might allow vectors, etc. So it's some sort of an SDP or a spectral relaxation. So the value, and it will be efficiently computable. And so the value it outputs is going to be an efficiently computable upper bound on opt. So the thing is that you could now, because we have some structure in our instance, we could imagine analyzing one such algorithm, some such algorithm on our instances and proving that it's not satisfied. Okay, and that's going to be our route. So a little bit in general on XOR refutation for random instances. So what is a random XOR refutation? So you have some n variables, little n variables, and you have a random Q uniform hypergraph. So the hyperedges are randomly thrown, and there are capital N such hyperedges, which are all equations. And for each such hyperedge, I will say that the corresponding variables in that edge add up to R. Okay, it's just that picture, but now it's no longer matching. It's some random hypergraph with many constraints. So here everything is random, and we certainly don't have this model. Okay, but there is another model which is studied called the semi-random model. But before that, one thing I'll comment here is that this, and your task is to prove that this instance is unsatisfiable with high probability. And note that this task gets easier as n is larger. If you have more constraints randomly thrown in, it's easier to refute. And one peculiar quirk in this literature on XOR is that the odd case, when Q was odd, was harder to deal with than the even case. So 3 XOR was harder than 4 XOR. And if you remember what I said about 3 query and 4 queries, this peculiarity was prevalent also in LDCs. Okay, that's also a bit of a connection. But there's another model called semi-random, where instead of random hypergraphs, which we certainly do not have, we have arbitrary hypergraphs. You can allow a worst case hypergraph, but the right-hand sides are still random. And now if capital N is big enough, your usual turn-off plus union bound honestly doesn't care about what the hypergraph is. It only cares about the right-hand sides being random. So it still works. But now there was a line of work on, can you efficiently do this? Right? Can you certify this always? And this is called the semi-random refutation model. And there has been some progress on semi-random refutation recently. So so what we showed with Abascal and Kothari is that if you give me enough constraints, note that even if you have 10n constraints, this will be unsatisfiable. But if you have way more constraints, like n to the q by 2, so say n to the 1.5, then in polynomial in n time, we can give a refutation of such an instance, which is non-trivial. And in a subsequent work with Kothari and Peter Manohar, we got a trade-off. We said that if you give me more time, I can reduce the number of constraints. So if in n to the L time, I can do this. So no need to read this, but the point is that if L is constant, you get back to this with polynomial time. If L is n, so you give me exponential time, then I can do pretty much optimally. And then there is a linear trade-off in the exponent in between these two regimes. And the nice thing about these works, both these works, is that it matches what was known for the fully random case when the hypergraph was also random. And in these very nice works by Raghavendra Rao Shram and also Wayne Alloway Moore, which in particular introduced this Kikuchi matrices to this thing, which was the key for our work. So it matched these things. So then our hope is, can we leverage this? And because if you look at our LDC XOR instance, we have these hypergraphs, which are arbitrary, and the right-hand sides are random. So it sort of feels semi-random, right? Arbitrary hypergraphs, somewhat random things, but it's not exactly semi-random because you don't have enough randomness and so on. So you cannot use those things as a black box, but it turns out you can use the tools nevertheless. Okay. All right, so with that, let me talk a little bit about the two-query LDC lower bound. So we said n is exponential in K, and this was shown using a quantum argument, and it was also shown for linear codes earlier in this work by Goldreich and others. And here's a spectral argument in the mold of q-XOR refutation. So a lot of these refutation algorithms in the previous slide, I said really use spectral methods heavily. And so I'll adapt that to this q-XOR refutation. I should say that this is well known, and this is another view of how basically was done in Kernidis, de Wolf, and so on. So to do this, but I think I just want to give this to give us some taste of some spectral thing, which is in the end what is going on in these under the hood. So now in two-query case, you don't have hypergraphs, you have graphs. And let me also make this switch from 0, 1 to +1, -1. So when you have an equation XU plus XV is Ri, you now have XU, XV is Ri. The product is Ri, where the right-hand sides are random. So you have k such graphs, and each graph has the same right-hand side. You have some such constraints. Now, you want to know what is the best solution you can get. Now, by standard conversion, the advantage of optimum over half, the largest fraction of constraints, is roughly 1 over the number of constraints, which is like n times k. You have k matchings of size n, times this big quadratic form, which is basically Ri, Xi, Xu, Xv. This is 1 when the equation is satisfied and -1 if it's unsatisfied. So just trust me that this is the advantage over random guessing. So this is kind of what you get. So that's the full expression over all graphs. And note that this is a nice quadratic form. It's X transpose AX, where A is the summation of Ri times AI, where AI is just the adjacency matrix of this HI. Okay. So if you don't, just trust me that it's this quadratic form, if you didn't immediately see it. And now that's how we are going to upper bound this, right? So we want X is an arbitrary ±1 vector. We want to maximize over it, but we just say that this quantity is at most n times the spectral norm of A, because X is a vector of norm square root n. So this is n times square root A, the n and n cancels. So your overall upper bound is spectral norm of A by K. Okay. Now A is this matrix. So note that the HIs are fixed graphs, but A is a random matrix because of the random signs. And now A is a very nice matrix, actually. In fact, these HIs are matching. So A is a very sparse matrix. So it has low spectral norm and so on. And by standard matrix concentration things, if you take a random signed sum of such matrices, which have low spectral norm, then its spectral norm will be low in expectation. In fact, the exact value you get is like log n plus square root k log n. When you're summing up k of these matrices, and n is the dimension of these matrices. And that's it. So you put this thing in, you get basically log n by k plus square root log n by k. So you can basically say that if k is at least log n by epsilon square, this entire optimum is at most half plus epsilon. So such an LDC cannot exist. Okay. So that's pretty much actually the, assuming this Bernstein, which is a standard fact, and it's a very simple setting of that, this is a full proof. Right? So, so that's how you prove the two-query bound. So how do we get to larger queries?
Okay. So I have a question. Mm-hmm. So why did you do max X over everything? Like, shouldn't X be just a code word?
No, that's the translation you made. At this point, you've forgotten about the code word everything. You mapped it to an XOR instance, and you will say there is no solution whatsoever. Because if there is a solution, you could have potentially taken that as the code word encoding the RIs, right? So, okay, so let's see. So for 4 queries, what can you do? I think I underestimated the time. Okay, hopefully in 10 minutes more, I'll say something, get to 3 queries. So if you want a 4 query lower bound, you can give a similar spectral bound using a bigger matrix of dimension n choose root n. And it effectively applies the previous 2 query bound to a bigger code. So I'm going to present this combinatorial reduction, which is also again from this previous work. And hopefully using that, I will later see how to tell you how to move to 3 queries. Okay. So how do you get a longer, so how do you do a 4 LDC lower bound? It will be by reduction. I say if I have a 4 LDC, which is this matchings of 4 hypergraphs, I'm going to somehow get a 2 LDC from it and then apply the lower bound. So how am I going to do that? So you have these matchings. Let F be all subsets of size square root 10 of these n things. So here is a basic claim. If I take a random subset of size square root n, and I have a matching of size omega n, with constant probability, I'll hit one of those matchings in exactly 2 edges, 2 points. So that's what is illustrated. S is a random thing, and this edge I hit in 2 points. And in this case, I can have another set also of size square root n, which hits this edge in 2 points, which is just XOR of S and E. That will be another set which will include these 2 points, right? And the other points. And note that that has size L2. And this is actually crucially where you use the fact that 4 is even. So this symmetry just breaks down when you try to do this with 3. And now why is that good? You could get the ith bit by XORing these 4 bits in E. But since S XOR T is E, I can also get those things by XORing, taking the XOR of all the bits in S, XOR with the XOR of all the bits in T. So if I define this notation XB to be the XOR of all the things in that set, this XE, which I want to decode the ith bit, is now the sum of XS plus XT. So essentially, instead of querying this, I'll just query these 2, and that's 2 queries. But how am I going to get XS? Well, I'm going to make my code have that. So basically, I will change my code to say that for every square root n size set, I will include the XOR of those things. This is some sort of like a direct sum or basically tensor product of this code. So I'll make a new code, C tensor L, which on every subset just XORs these bits. And now by this argument, trust me that this is a legitimate 2 query LDC, albeit much longer. But now I can apply my 2 query lower bound. This code is longer. It is n choose L long, but my K is at most log of the number of length of the encoding, which is n choose L, which is at most L log n. L was square root n, and we got this bound. And why did the square root n come in? Maybe I should quickly say a few words. The thing is that let's just imagine you sample each point with probability, say 1 over root n. Then the chance that you pick exactly 2 in a single edge is 1 over n. And then there are omega. So at least in expectation, you will have many edges with exactly size 2. And because this is a matching, you will get, this also will happen with decent probability, and you get an n. So that's the idea. So basically a random size, square root n is the correct point where you will expect this to happen with probability square root, omega 1. Okay. Okay, let's try to do 3 query LDCs. Now the same thing happens. Same picture, I XOR these 3 things to get this particular value. But now the previous thing doesn't work. Or what is the big O hiding in the previous slide? You mean the last thing? O tilde, O, I'm hiding some logarithmic factors here, depending on it. Okay. Maybe they won't even exist in this case, but I was just being safe. So for 3 query LDCs, we again borrow. So there's another trick which is very natural in XOR refutation, which we'll borrow. So if you have 2 equations which share a variable, then I can add those equations, that variable goes away, and I get a 4 XOR equation. Okay, so if I have 2 such. So if I have, so of course, inside a matching, the hyper edges don't share with each other, but across matchings, they might share. So if I share something, I can resolve on that, I'll get this equation. So now you have K matchings, each of size n. So a typical Xi is actually present in K hyper edges across matchings. So when I do this resolution on each of these, I'll produce K square constraints. If I do it for all the n variables, I'll get about n times K square XOR constraints. And note that in the 4 LDC case, I only got n times k constraints. Now I got n times k squared. So I got more constraints, so that's good. So maybe that helps me to refute it better. And there is this annoyance here that it's not exactly Ri, but there's a trick there, which is that you can randomly set half the Ri's to 0. So half of them will remain, and now you can just focus on those things which are unset. And for those, basically you'll get 4 uniform hypergraphs, each having nk hyperedges XORing to this. Okay. So again, it's really the same picture as before, as in the 4 XOR case, but and now you have these hyperedges, hypergraphs of 4 uniformity. So can we just try to do the previous 4 LDC approach? And pretty much the change, of course, here is that now you have nk hyperedges, not n. So of course, it's not going to be a matching. It's going to intersect in all possible ways, maybe. So, but we have many more hyperedges. The question is, can we do this, use this? And then this is really the key point where the gain comes. Now, earlier we picked a set of size n over square root n, but now we have k times more edges. So we can actually sample a smaller set of size square root of n over k and still expect to hit many edges. So we can expect to hit many edges with probability, the constant number of edges exactly twice. Okay, the same expectation argument holds. If we can also guarantee that happens with decent probability, then we will be done as before. Okay. And this is where things get a little technical, because the concentration property was easy for matchings because the edges didn't interact at all. So you could use some independent things, but now the hyper edges might cluster a lot. So there is a chance that your expectation may be large because you might pick these 2 things, which is in this sort of sunflower-like structure. Whenever you pick it, you get a big value to the expectation, but the chance that you pick that might actually be very small. So some crazy clustering of these hyper edges will interfere with this argument. So, and that's the final ingredient. We can somehow avoid, we can prove that that doesn't happen. So if you have these hyper graphs, what we can prove is that, so we can prove that for most of the pairs, they will not together occur in too many hyper edges. So of course, each of these are matching. So a particular pair occurs only one hyper edge per matching, but you can ask in how many hyper edges does it occur together across these matchings? And there are k such matchings, but we can prove that it will not occur in more than log n things. And if you assume this regularity, then the same argument as before goes through, and you can sort of believe it because you're saying that pairs don't occur together in too many hypergraphs. But of course, how do you ensure this? And for this, again, there is this trick that if you have a pair xj prime occur in 2 hyper edges, hi and hi prime, and they add up to these things, I can add those things and both of them cancel. So instead of getting a 4 XOR equation, I actually now get a 2 XOR equation. And once again, there is this thing that you can set half of the variables to 0 to make the right-hand sides just be single things. So again, the qualitative fact is that if you have a violation of this regularity, you can actually produce a 2 XOR instance with many constraints. And we kind of already have shown before that if you have such 2 XOR instances, that will force k to be at most log n. And we are only trying to show that k is at most cube root n, right? So that's the overall argument, okay? Yeah, so it gets a little bit technical to show this regularity and interface it with that concentration, but that's the idea. So I'm already over time, so I think I should wrap up, but this is all I was basically going to say anyway. So our main result is that we got a k cube lower bound for 3-query LDC. And the way we did this is that we produced from this LDC a 4 XOR instance with more constraints than you would get if you started from a 4-query LDC. And that gave us an improvement compared to the 4 LDC case. And this was heavily inspired by recent progress on semi-random CSP refutation, even though in the end, you can give a presentation of this. And pretty much that's what I did here in a more combinatorial viewpoint as essentially a reduction. You try to reduce 4 LDC to 2 LDC was a very clean reduction. And essentially, we're also giving a reduction from 3 LDC to 2 LDC. But that reduction is best explained in the context of these XORs. It's doing some steps which are much more natural in the XOR world than in the LDC. But ultimately, it is a reduction of some form. And one annoyance and quirk of our proof is that we show 3, we improve it for 3, but for 5 query, the best bound is the same as this, what is known for 6 queries. Right? So, and that is, which is this n to the q by q minus 2 for in general. Okay. And the issue, the reason we're not able to do that is that this last technicality of establishing or justifying this regularity assumption doesn't really work. So once you have more queries, it's possible that pairs occur together in many more constraints, and that gets tricky. Okay. So there are many challenges. So maybe I'll quickly. So one thing is to remove this quirk and actually get this lower bound for all odd q. Other obvious question is that there is still a huge gap between the lower bound and constructions, close it in either direction. Outstanding open question is that can you make polynomial length LDCs with constant queries? Okay, so I don't think there's the conjecture either way. And these two things are things I didn't quite cover in the talk, but I'll just leave it out there. So in case somebody wants to discuss it, we can do it. But one is, what is the story with LCCs? There, all these matching vector-based improvements don't apply. And also our ability to prove lower bounds for PIR, which is related to LDCs, essentially like LDCs over big alphabets, has also been pretty limited. That will also be nice. Okay, so I think I'll stop there.
Okay, well, thanks, Venkat. Let me take us off the recording, and we can stay hanging out and asking questions.